Salutations to dear evaluators. My name is Diana Chong binti Muhammad Amirul Solehin Chong. Today I would like to talk on my review on silica nanoparticle for pericularia oryzae management, recent developments, challenges, and prospect. For the introduction, one of the most dreadful diseases for paddy plant is rice blast disease. This disease is caused by the species of fungus called pericularia oryzae. Alternative way besides fungicide in overcoming this disease is by using silicon. The use of silica nanoparticle is the latest technology in silicon application in controlling this disease. Next, we have four objectives here, which are to review the establishment of ideal characteristic of silica nanoparticle for plant usage against pathogen. Next, to study the interactions between silica nanoparticle and other components and the effect on its delivered efficacy. The third one is to dissect on the resistance induced by silica nanoparticle against rice blast disease. And the fourth one is to analyze the challenges and suggest the solutions to overcome it. Moving on to the next slide is the advancement of silicon usage in agriculture through silica nanoparticle. First, I will explain on the advancement in which silica nanoparticle is a form of silicon that is in nanoparticle form. The characteristic of nanoparticle is that it has bigger surface area compared to normal size of silicon particle. This means that low doses of application is needed to deliver the efficient amount needed for the plants. Next, in this framework, we can see the production of silica nanoparticle from rice husk to amorphous porous silica nanoparticle, which is the primary nanoparticle. And then it undergo potassium nitrate treatment to promote the melting of silica nanoparticle to form porous structure. After potassium is introduced through potassium nitrate, different concentration of potassium nitrate introduced can enhance the crystallinity of the silica nanoparticle, and this enable them to be tuned into desirable pore size and microstructure that is more suitable for wide, including for rice blast protection. Moving on is the interaction of silica nanoparticle with some components of the soil. The first one is the interaction of silica nanoparticle with fungicide. It is reported that silica nanoparticle application alone is as effective as the application of fungicide. However, the efficacy depends on the nitrogen level in the soil. Next, the combination of silicon and fungicide is also reportedly to be the most effective in controlling rice blast disease. The bar chart below shows the comparison between the efficacy of several treatments in treating rice blast disease. As you can see, the lowest rice blast infection, which is 16%, is shown by the mixture of application of silicon and benomyl, which is a type of fungicide. Next is the interaction of silica nanoparticle with fertilizer. The interaction shows different efficacy when combining with NPK fertilizers. The application of NPK fertilizers reduce the amount of phosphorus content induced by silicon application. Next, it also causes spike in nitrogen content that is unfavorable for rice crop to grow because it creates higher risk for rice blast infection. This shows that NPK fertilizer and silica nanoparticle does not work well together. The next and the last interaction is between silica nanoparticle and earthworm. Silicon works well with earthworm, but only without the presence of NPK fertilizers. This is because earthworm helps in releasing of nutrients bit by bit compared to NPK fertilizers that often causes nutrient spike. Moving on is the resistance induced by silica nanoparticle against rice blast disease. The first method of resistance induced by silica nanoparticle is through the formation of physical barrier. The formation of dense layer of silicon beneath the cuticle of the leaf provides protection against the penetration of Pericularia oryzae. The second resistance induced by silica nanoparticle is through biochemical mechanisms. One of the mechanisms is through the activation of defense-related enzymes such as chitinase, polyphenol oxidases, and phenylalanine ammonialyase. Another mechanism is through delaying fungal invasion through dense silica nanoparticle deposition to allow production of myrmilactones, which is an allelopathic and stop the invasion of Pericularia oryzae. The third and the last resistance is through molecular mechanism by triggering the defense genes activation. This genetic activation causes various modifications such as lignin biosynthesis, protein synthesis, and stress tolerance against pathogen attack. These modifications are all essential in protecting rice plant against rice blast disease. Next, before we move on, here is the brief detail on rice blast disease. It is caused by fungus Pericularia oryzae. It infects by depositing its conidia on the rice tissues, and the deposition of conidia is higher when the relative humidity is high. Moving on is the usage of silica nanoparticle as cultural approach in suppressing rice blast disease. As a cultural approach, the most current effective concentration of silica nanoparticle solution to suppress this disease is at 200 ppm. Next, silica nanoparticle can be applied through root and also foliar application. However, soil applied silica nanoparticle is proven to be more effective. This is because silicon accumulation through foliar application is way lesser compared to root application. Foliar application also lacks in systemic acquired resistance by plant, such as through the biochemical mechanisms aforementioned before in the previous slide. Okay, the last topic is on the challenges and future prospects of the usage of silica nanoparticle in handling rice blast disease. The first one is the knowledge of using this technology is not widely known for farmers, because this is a safer approach in controlling rice blast disease compared to fungicide. Next, manufacturers of silica nanoparticle should improve in obtaining better source of silica nanoparticle. Agricultural waste such as rice husk and corn cobs are better source compared to silica slag that might contain heavy metals besides being pricey. The third one is more research in creating rice varieties that performs better in accumulating silicon should be done to minimize the cost and amount of silica nanoparticle application. And the last but not least is more studies in creating a better formulation in terms of concentration and size of silica nanoparticle for better efficacy should be done to control rice blast disease. These are the references for the infos mentioned in this presentation. Therefore, that concludes my presentation on the usage of silica nanoparticle in handling rice blast disease. I hope those were delivered clearly, and I thank all the evaluators for spending your time listening to this presentation. Thank you.